Assalamu alaikum. Synchronous motors have one problem, that is, these motors are not self-starting. So in today's lecture we shall discuss this problem in more detail, and we shall also talk about possible solutions to overcome that problem. That is, we shall learn how to make a synchronous motor self-starting. So we know that there are two magnetic fields in a synchronous motor, Bs, that is due to currents in the stator winding, and that stator magnetic field is rotating with synchronous speed. The speed of rotation of this stator magnetic field, that depends upon the frequency of the currents which are flowing in these windings. This Br is due to field windings on the rotor, and due to interaction of the two magnetic fields, a torque is induced. That torque is given by, that is, induced torque will be such that it will tend to align both the magnetic fields. What will happen initially? This rotor will be stationary, this Bs will be rotating, and the induced torque, there will be some induced torque which will tend to rotate the rotor. However, this rotor has some inertia, and due to that inertia, the rotor cannot quickly gain acceleration to catch up this stator magnetic field. Therefore, this will fail to rotate. Let's elaborate this point with the help of diagrams at different time instants. So here we have the rotor. We have this rotor, and there is a rotor magnetic field, Br. And at time instants, let's call it omega t equal to 0 seconds, this is the vector for Bs. Bs is rotating at a certain time instant. It will have this orientation. And how much will be induced torque? Induced torque corresponding to this time instant. Since both the vectors are parallel to each other, therefore induced torque is 0. Let's analyze the next time instant. Since rotor has some inertia, it has not rotated, it is still at the same position. Bs, that is rotating with synchronous speed, and at time instant omega t equal to 90 degrees, it has rotated by an angle of 90 degrees. And what is induced torque corresponding to this time instant? Direction of induced torque, Br cross Bs, that is Br cross Bs is in counterclockwise direction. There is a non-zero induced torque which is in counterclockwise direction. At omega t equal to 90 degrees, induced torque is in counterclockwise direction. Next time instant, although here torque was non-zero, it was in counterclockwise direction. However, the rotor has its inertia, and this stator magnetic field has quickly moved to new location. This one, this is stator magnetic field, and rotor will not rotate. We know that this stator magnetic field, for example, if you have supplied a 60 Hz voltage source to this stator, then this stator magnetic field will complete 60 revolutions in 1 second, and so that time is quite small, and rotor will not rotate by a significant angular displacement, and this stator magnetic field will have rotated to new orientation. Rotor magnetic field will be still in the same, almost in the same position. And now what is situation? The two magnetic fields are antiparallel, and therefore induced torque is again equal to 0. Induced torque corresponding to this time instant, that is equal to 0, that corresponds to omega t equal to 180 degrees. What will happen at the next time instant? This rotor has still not rotated by significant angular displacement. Therefore, rotor flux density vector is still at the same orientation. However, stator flux density vector has rotated by another 90 degrees at omega t equal to 270 degrees. So this is stator magnetic field. Corresponding to this time instant, how much is induced torque? Induced torque is again non-zero, but now it is in clockwise direction. So this cycle will repeat. That is, during one complete rotation of this stator magnetic field, the induced torque will change its direction. Initially, it is in counterclockwise direction, then it is in clockwise direction, and then again counterclockwise and then clockwise. So what will be average torque? Average torque, that will be equal to 0, because at some time instance it is counterclockwise direction, at other time instance it is in clockwise direction. Induced torque will be, average induced torque will be 0, and therefore rotor will not rotate. And due to changes in the direction of induced torque, there will be high vibrations in the rotor, and that will not only damage the mechanical setup, but will also cause overheating in the motor, and therefore it will damage it. So that is, synchronous motors are not self-starting. What are possible solutions? There are three possible solutions that are listed over here. So here are three possible solutions to make a synchronous motor self-starting. That is, reduce the speed of stator magnetic field. That is, reduce the frequency of the voltage which is supplied to stator windings. The second solution, use external prime mover, which will bring the speed of the rotor to near synchronous speed. And third solution is use damper windings. We shall talk about all these solutions one by one. So the first possible solution is to reduce the electrical frequency of voltage which is supplied to the stator windings. We know that this speed of rotation of this stator magnetic field, that is related with the frequency of the supplied voltage. So if the frequency is very high, this stator magnetic field will rotate very quickly, and rotor will not get enough time to catch up the stator magnetic field. However, when the frequency of the supplied voltage is reduced, then stator magnetic field will rotate slowly, and therefore induced torque will cause this rotor to rotate, and this rotor will now have enough time to rotate and catch up this stator magnetic field. Once this rotor gets some speed, we can gradually increase the frequency of the supplied voltage to bring it to the rated condition. So this is one possible solution. The disadvantage is that you need additional electronic circuitry that will increase the cost of the motor. And there is one precaution. We know that the generated voltage, internal generated voltage, EA, that is dependent upon the omega, that is speed of rotation of the rotor. And we also know that the current which flows in the armature winding, you know the equivalent circuit of this synchronous motor. This is armature circuit, and if EA is small, then IA, excessive current, will flow through the motor, and if current higher than the rated current flows, that can damage the motor. Therefore, to keep the current within limits, we have to reduce the supply voltage, magnitude of the supplied voltage. So as we decrease the frequency of the supplied voltage, we should also reduce the RMS value of the supplied voltage which is connected to the stator winding. This is first possible solution. The second solution is use external prime mover. We can use some external mechanical arrangement to initially connect it to the rotor. This prime mover will rotate the rotor, and will bring it to near synchronous speed. And once the rotor gets near synchronous speed, and then it will be able to catch up this stator magnetic field, and we can remove this external prime mover. This external prime mover can be another small motor connected with the rotor, and we can initially disconnect the mechanical load connected to the rotor to this motor and connect this small motor, and that small motor will rotate the rotor and bring it to near synchronous speed. The required motor over here is small compared to this original synchronous motor, because this small motor has only to carry the load of the rotor, and then once it gets near synchronous speed, we can connect external mechanical load to this synchronous motor. So this is the second solution. However, again, it is associated with additional cost. You need additional motor to run this synchronous motor. Third solution is damper windings. This third solution is the most popular one, and it is also low cost solution, and we shall talk about this solution in the next lecture, inshallah.